So now let's take a look at problem 522. Okay, so an organism of the genotype, let me see, AA, BB, CC was test crossed to a triply recessive organism. You can probably guess what that is, right? So 2 little a's, 2 little b's, 2 little c's. And then the problem lists us 8 different genotypes here that are seen in the progeny. But before we get to that, what it asks us to do in part A, so we're going to assume that these 3 genes are assorting independently. And if they are, how many genotypic and phenotypic classes would result in the offspring? What proportion? And we're going to assume simple dominance and recessiveness in each pair of genes. Okay, so if these are assorting independently, if they're assorting independently, then what does that mean? Well, we already know all the gametes from this parent over here are going to be A, B, and C. Only one possibility for those. So what about these over here? Well, so if they're assorting independently, so 1/2 can have a big A, and 1/2 can have a little a. So we're getting back to, the first section of the course, where we talked about independent assortment and using the fork line method to figure out all the different possibilities of genotypes in the gametes when all the genes or alleles of genes assort independently of one another. So of those A's, 1/2 can be big B, 1/2 can be little b. Of these B's, 1/2 can be big C, 1/2 can be little c. Okay, and that's the forked line method, and we can go down and we can do this for all the alleles. And you can move this down a little bit, this A, so I can map this out. 1/2 of those little a's can be big B, 1/2 can be little b. Big C there, little c there, and 1/2 big C there, 1/2 little c here. Okay, we can multiply across, and what we're going to see is that 1/8 are going to be 1/8 of the gametes from the heterozygous individual are going to be big A, big B, big C. 1/8 A, big B, little c. 1/8 big A, little b, big C. 1/8 big A, little b, little c. And then we're going to kind of replicate this again just for little a's in every big A position. And I just have this pattern memorized, but you'd get these patterns if you multiplied those fractions and across and combine the letters appropriately. So little a, big B, big C, little a, little b, big B, little c, little a, little b, big C, little a, little b, little c. Okay, so we have 8 possible gametes here, right? Let's see. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so I'm going to copy these first 4. I'm going to move these down. Copy, and I'm going to paste those right over here. Excellent. And I'm going to take the other 4, copy, and I'm going to move those down right over here. Okay, now we are going to fertilize each of these with this gamete right here, right, this ABC, because that's the only type of gamete that could be made from the other parent. And so these are the genotypes we're going to get in all of the offspring. Now, because of the way I'm putting these together, we don't have the A's right next to each other, we don't have the B's right next to each other, but we can determine the phenotypes still, even if they're not written out nice and neatly and organized. So these are the genotypes we should get, and so we can actually use these to calculate the phenotypic ratio. So let me actually copy this so I can shrink this down a little bit. Copy and paste, and I want to shrink this just a little bit, not that much. Okay. Now, let's take a look. So these right here, can we combine any of these? Let's see. Okay, so these are the same. Nope, this is a little c. These are all unique, right? Yes, so these are all unique. So what we're getting here is 8 different genotypes in equal amounts. So they're all going to be represent about 12.5%. So if we were looking at 100 progeny, well, we'd probably see 13 here, 12 here, 13 here, 12 here. You know, one of them's got to be 12, one's got to be 13. You can pick and choose as you wish. Okay, so now to reiterate a little bit here, I'll clarify some things. I'm going to change the color of my pencil. Let's see. Okay, so if A and B and C are genes that are sort independently during meiosis, then these are the genotypes we should see from that cross of an individual who is heterozygous for all 3 crossed to an individual that is homozygous recessive for all 3. Each one should be found in about 12.5% of the progeny. Each genotype should be found in about 12.5%. Now, the problem gives us some data, and I'm going to paste, let me see, I'm going to paste something in here. Okay, so these are the actual numbers. So let's take a look and see how they compare to our data that we get when we assume independent assortment of all 3 alleles of all 3 genes. So now let me find a nice color. How about pink? Let's try pink. Okay, so 20 are going to be heterozygous here. So let's see if we can find the heterozygous. Okay, right here. So we should see 20 of these. That's a 20. And 20 are homozygous recessive for A and B, and heterozygous for C. So let's see if we can find those. Heterozygous for C. Right here. So 20 should be here. I keep writing 22, I don't know why. But 20 should be there. And 5 should be recessive for, homozygous recessive for B, and heterozygous for A and C. Now let's find that one. I think that's this one, right? Yes, that's this one. So 5 should be this one. And then 5 should be homozygous for A, homozygous recessive for A, and heterozygous for B and C. Let's see if we can find that. Oh, right here, 5. Okay, so you can already see our numbers aren't matching the actual observations. So clearly that it's all 3 genes are not assorting independently. So no independent assortment, I guess, for all 3. There seems to be some linkage going on between at least 2 of the genes. Okay, so that's part A. Now let's go on to part B of the question. Now with part B, okay, so part B is answer part A again, assuming the 3 genes are so tightly linked on a single chromosome that no crossover gametes were recovered in the sample of offspring. Okay, so this is a little easier, I hope. So let's see. Again, we're crossing individual with that genotype to an individual with this genotype. Now these can only make one gamete here, one genetically distinct type of gamete. And here, if all these are tightly linked, well, I guess we're going to have to assume we're going to put all big A, big B, and big C together, little a, little b, and little c together. So these are so tightly linked here. We're assuming this arrangement of alleles. Let me clarify that for you. So if they're linked, we have to assume an arrangement to get started. So we're going to put the dominant alleles all on one chromosome. It doesn't have to be like that, but we are going to start with that assumption. And the recessive alleles all on the homologous chromosome. And though if these are so tightly linked that there can be no crossing over, then we can get 2 types of gametes only. Big A, big B, big C, little a, little b, and little c. And before, we had 8 types of gametes, right? And they were all found at a 12.5% frequency. Here, we only have 2 types, so out of 100%, 50% are going to be this genotype, 50% are going to be that genotype. And so we can combine these with this gamete from the other parent. Okay, before, when they're sorting independently, we had 8 different genotypes in the offspring, found at equal ratios. But now, in this case, we have only 2 genotypes in the progeny. Half of them are going to be heterozygous when we combine this gamete with that gamete. And the other half are going to be homozygous recessive for all 3. And we can paste in the actual data again. Let me see. How did this work before? Okay, paste from... Okay. Pasted that in, and we can compare, and you can see it's very different. If they were so tightly linked, we would see only 2 genetically different types of progeny as a result of crossing these 2 parents up here. 50% or 50 out of 100 would be this genotype, and 50 out of 100 would be this one. Okay, so clearly from part A we can see that these 3 genes are not assorting independently of each other. At least all 3 of them are not assorting independently of each other. And these three genes are not so tightly linked that crossing over, at least crossing over must be happening between some of them, because the tight linkage hypothesis between all three genes does not play out either. So for part C of this problem, now I haven't thought this all the way through yet, but let me try something. I'm going to see if this works with one take here and see if I can figure this out. So I'm going to paste in the original data again, and what I'm going to do is try to find a pattern here. Okay, so what is part C? So part C is, what can you conclude from the actual data about the location of the three genes in relation to one another? So we decided that they weren't all sorting independently, so they're not all so close together on a chromosome that they are showing linkage. Again, they're not completely linked either, so there is some crossing over going on between at least a couple of these. So I'm going to try to look for a pattern between these so I can try to figure out what's going on. Now remember, we are crossing triply heterozygous to homozygous recessive. And so the homozygous recessive is going to donate an a, small b, small c, no matter what. So maybe we can eliminate the small a, small b, and small c from the genotypes up here. Just eliminate those, and maybe that'll help us see a pattern. So eliminate the small a, small b, and small c, and that means, you know, whatever's left, that's what's coming from the heterozygous parent. So 20 big A's, big B's, big C's, 20 little a, little b, little c, so I'm just going down 1, 2, 3, 4, like that. 5 big A, little b, big C, 5 little a, big B, big C. Okay, let's go to the other side here. 20 big A, big B, little c, 20 little a, little b, little c, 5 big A, little b, little c, 5 little a, big B, little c. Okay, so these are the gametes that are coming from the heterozygous parent. And let's see, do we see any patterns here? Well, okay, I see one thing right here. Oh no, I messed this one up. This should be a big C. Okay, see nothing so far. Okay, what do you see? Maybe you see it already. Don't tell me. Don't tell me if you see a pattern. I'm thinking about this. Okay, I think I see something here. We have 20 progeny over here. We have big A and B, big B. 20 over here with big A and big B. We have 20 over here with little a and little b. We have 20 over here with little a and little b. So right away we're starting to see most of the gametes that are being made by the heterozygous parent have the big A stuck together with the big B and the little a stuck together with the little b. So when we compare that, when we think about that a little bit more, so if the arrangement was something like this in the heterozygous parent, big A and big B linked together on one chromosome, little a and little b on the other, well then we'd expect big A to be found with big B more often in the gametes than we would with little b, and we expect to find little a with little b more often than little a with big B, and that's what we see. And then crossing over should happen with some frequency, but we should see the crossing over gametes less than we should see the non-crossover gametes. And I think that's what we see. I'm going to use green down here. So here we have a big A with a little b, and a little a with a big B, and that's 5 of the offspring. And over here we have another 5. Big A with little b, and 5 little a with big B. Okay, so I think this data is telling us that A and B are linked, and this is the arrangement. This is the arrangement of the A and the B alleles in the heterozygous parent. What else can we determine here? Can we determine the distance? Okay, so we have 100 progeny here total, right? So 20 here, 40, 45, 50, 70, 90, 100. So out of 100 progeny, 80 of them are showing are the result of no crossovers between A and B, right? So we have 20 here, 40 here have big A and big B together, and 40 have little a and little b together. 20 must have resulted from recombination between those. So the distance between A and B is going to be 20%, or 20 centimorgans. So 20 centimorgans between A and B, which are linked on a chromosome. And the arrangement is big A with big B on one chromosome, and little a with little b on the homologous chromosome. So what about C? Okay, well, let's look at C. C doesn't seem to be stuck with either A or B, right? So we have C, a big C, with 20 big A's and B's, and another big C with 20 little a's and little b's. And then we have 5 big C's with a big A and a little b, and 5 big C's with a little a and little b. So there seems to be, no correlation here between having a big C allele and the genotypes of A and B. Also, 50 of the progeny have a big C allele. If we look over here, the same thing with the little c's. Little c is found with all of these. So with the 20 big A's and big B's, 20 little a's and little b's, 5 big A's, little b's, 5 little a's, big B's. And it's found in 50 of these. So that's telling me that C is assorting independently of A and B. So for this question, and why is it sorting independently? Because we don't see either the big C or the little c found predominantly with any of the genotypes. We find it at equal frequencies, like it's assorting independently of any of the other alleles. So what can we conclude from the actual data? So we can conclude that A is linked to B that's the arrangement of alleles in the heterozygous parent, and A and B are 20 centimorgans apart. C assorts independently, almost as good as my writing in class, I know. Assorts independently of A and B, so it must be on a different chromosome or found so far away from A and B on the same chromosome that it essentially assorts independently. Okay, so that's the answer to 22. That was a little harder than any of the other questions we've covered so far, and please come see me if you have some questions about this problem, and any problem, of course.